We've all heard in science fiction novels how someone travels away from Earth at close to the speed of light and comes back in the future and he is younger than everybody else. And though there are a lot of scientific issues to that exact scenario, it is basically true to a concept of special relativity, which is time dilation. Now I'm going to explain this in a basic scenario. Let's say you have a moving car, but it's at rest. And here's a setup in the car. You have a light which shines up to the top of the car. There is a mirror attached to the top of the car, and there is a detector right next to the car, to the light, which knows exactly when the light comes out of this this light bulb and exactly how long it takes to reach the detector. So the light travels, bounces up and down. If the height of the car is h, then the time it takes for this light is rate times time equals distance. Here the rate is c, which is the speed of light, which we define as 3 times 10 to the 8th meters per second, the fastest anything can go, times your time equals, and your height, your distance is up 1h and down 1h. So your total time is 2h over c. Now let's look at the same situation, but have the car moving now. There's a dude in here who checks. Now the car is moving, and let's say the same process happens, but because the entire frame is moving, then from people on the outside who are observing this event, let's say there's 3 people, each timed exactly to each other, then the light does, from this guy's point of view, the light goes straight up and straight down. But from these 3 people's point of view, it actually moves in an angled path. So we'll see how that looks here. There's a guy inside confirming that even though this train is moving now at a velocity v, he still sees the exact same event as if this train were not moving. This is something that was postulated in special relativity. But look at what this light looks like, saying these are the train as it's moving. It shoots up here, hits the mirror, and then lands there. So what's the difference here? Well, here it's going straight up and down, but from an outside viewer, which means we're changing the reference frame, it's moving far diagonal to the right and far diagonal to the left. And of course, this is assuming v's very, very close to c. But, however, because this is the same initial frame, we know that the time should be the same for these people. So what is actually happening here? There has to be a change, because this c is moving at the same velocity, but seems like it's traveling farther to the outside people. Well, let's look at this mathematically. Let's look at this triangle right here. We have h, we have your velocity. We know that velocity times time equals distance. And this distance is going to be half, because we're only looking at half. So this is going to be vt over 2. And this is ct over 2, because this beam is traveling at the speed of light and we're taking half of it. So if you solve this out, you get interesting equation. The t outside is equal to the proper time, which the time it takes for this event to happen, times 1 over 1 minus beta squared. Beta is v squared over c squared. I'm sorry, theta is V over C. So beta squared equals V squared over C squared. What does this mean? Look at this value right here, V over C. Because V is always less than C, B is going to be a number less than 1. Which means 1 minus B is going to be a number barely under 1. Which means that this entire value under here is going to be less than 1. Which means 1 over this value is going to be greater than 1. Multiplied by the original times means that the time it appears that it takes for this event to happen to outside observers is longer. So this explains a lot of things, like, technically yes, if you were to be able to travel at ridiculously high speeds, then someone that stayed inside with that event taking place, say it's just a clock, is going to notice that they're ahead of time. Because to an outside viewer, that event, which really did take place at a normal time, appears to happen slower. So one way that the United States ended up testing this was, once jet planes became reliable, they took clocks, atomic clocks, so they could be precise. They put them in jets and flew them all around the world, many, many times. And when they came back to the Naval Academy, they compared these atomic clocks with clocks that had been in place in their laboratory. And what did they find? It was off by a couple nanoseconds, about 2 nanoseconds. But it was exactly in accordance with what they thought would be the change, based on the equation.